Hello, everyone. So continuing from last week, where we already talked about intro to machine learning. For those who could not there last week, which is going to go on you. Make sure to just check it out on YouTube. We post YouTube recordings of what we do. But anyway, this week we're going to be talking about neural networks. So first things first, recall from last week. We've already started. So we recall from last week that like unlike traditional programming, machine learning is where you put answers and data in and you try to get them. Traditionally, you know the rules, cook those up, that's what it is. And then you give in the data and you get some answers out of it. But what machine learning is trying to do, we're trying to get these rules, also known as a model for predicting what sort of answers we should give to these specific data points. But with that said, if you pose a question to you, I'm saying the word model, like in terms of what your intuition, what would a model look like? Like what sort of form would it take? And if you guys say Tom Brady's wife, I will slap you. So, really though, what sort of form do you think a model would take? Like, what sort of properties would it have? What's it supposed to look like? I don't know. What would you guys think? Do you not have to raise your hand, by the way? Shut up.
I don't know, representation of like data.
Yeah, so some representation of data, sure, yeah. Like I guess first of all, like what should it take in? What should it take out? Anyone have anything? Nope. Okay, cool. I will just I haven't checked this in chat. Whatever. Anyway, I'll just go with it then. So I mean, I guess we can think of it first like a model. Like first of all, we want it to be able to take in like the inputs and give us answers, right? Like that's a pretty obvious one. We want it to be able to take in the inputs and give us some sort of output. We also want it to be, I guess the word would be like it needs to have some sort of parameter, or it needs to be learnable is the term, right? Because like for example, you can't just, I mean, we can just say like, okay, cool, like there's like X rules to get from this input to this output, right? But if we can't put them in some sort of form into a computer, or if we can't recognize them over time, then something like that would be absolutely useless, right? We can't just come up with abstract human concepts of like a rule and say, okay, yeah, this is our model, because we don't necessarily know specifically how we're going to be able to make something, how we would be able to put something like that into a computer, right? So in general, we just want some sort of learnable thing that will take in an input and give us some sort of answer based on what our output is, right? So, as mentioned earlier, we can think of them as functions. What we have is a set of inputs, x, just letters, notation, don't worry about it. If you're mathematically inclined, you'll have fun with that. If not, then you have a set of inputs, which is all possible items that you want to throw into the model. So in the case of, let's say, trying to predict whether or not someone has diabetes, that would just be like vital signs and things like that. We have your set of outputs, which is all possible labels. So in the case of diabetes, whether or not they have diabetes, that was pretty easy to ask. And what we want is we want some sort of model or some sort of rule set, whatever, that can take some given example from X and map it to some label Y, right? And as mentioned earlier, yeah, this is exactly the definition of how functions work. They take something from one set, map it to another set. So what we're going to be doing is we're going to be representing these models as some sort of function, right? So some thing to just take something from your set X, so some input example, and maps it to one of the labels that you want to. So with that said, let's just out of the blue, I'm sure a lot of you have learned this in algebra 1 or something, a linear equation, right? Just start off with that in mind. So well know what linear equations do. I'm not going to talk to you about that. But first of all, from what you guys remember from when we had to do anything like this, what makes linear equations useful in terms of modeling relationships? I will accept grade A answers to this, frankly, they are very specific. Yeah, exactly. So it shows the relationship between two variables. Specifically, it's a very easy to show the relationship between two variables, right? You just have a bunch of different input things you'll have. So in the case of diabetes, heart rate, blood type, I don't know, stuff like that. And you just throw it in, and based on how important each aspect is, so for example, blood pressure may be more important than someone's age when figuring out if they're diabetic, right? You would just weight them accordingly based on these weighting coefficients here, and you sum that all up with some sort of line or something. And weight that away. and you get some sort of linear model as you get some sort of output, right? Now, obviously, we use linear equations all the time. They're extraordinarily useful for just modeling relationships. But think about the kinds of models that we're talking about, right? We're not tackling simple things just like, how like price increases and more people come over to your school or whatever, to your store, school. Anyway, as more people come over to your store, like we're not just modeling something simple like that. We're trying to model like complex relationships, right? Like given someone's vital sign, do they have diabetes, or like given a certain condition of like a business, what is the stock price going to be like in the next couple months or something, right? These are not linear relationships, as you guys very clearly understand. They're very highly non-linear in that they're dependent on a lot of different things and they're not directly dependent on it. There's like multiple different ways they can go through and a whole lot of different issues that come in. So while these are useful and simple and really easy to write down and understand, right? They don't really work for our sake, except for like very, very, very simple cases, because we are trying to model non-linear relationships. So let's take the dumb approach, which is, I said the dumb approach is actually what we do, and let's just kind of throw a non-linear function over it. So we've got some function g, could be x squared, could be, I don't know, like the reason zeta function, I don't particularly care. Could be whatever the heck you want it to be, just some sort of non-linear function. In fact, it doesn't actually need to be non-linear. It could just be any function, right? And then let's run our linear models output through that, right? We can call that whole setup a neuron, but what we've done here essentially is this function g allows us to model non-linear relationships. So if we have so we're using this sort of model for like a specifically linear relationship, you just set g to be the identity function, just that's and then you're done, right? No issues there. But if we're trying to model something a little more something that's more non-linear, we can set it to something that is non-linear, like something like x squared. I mean, look, commonly none of the functions I'm about to say are like ones that are used. You use like hyperbolic tangent and sigmoid and other weird things like that. But that actually isn't too important for understanding what a neural network is. You just need to know that it's just some sort of function that basically allows you to take your linear model's output and map it to some sort of non-linear relationship. So we have this intermediary that allows us to model these non-linear relationships that we see. And then in terms of terminology, let's just call this whole setup a neuron. You guys can see this. And you've got a bunch of weights, which are W1s or whatever that. You've got your bias term B, just a y-intercept. Don't really know why it's called a bias term. This doesn't like maybe belong to bias in some way or the other, but like it's called a bias term, so we're doing it. And then G is your activation function, specifically just that non-linear function that allows you to model non-linear relationships. We call it an activation. And so we can diagram this as such, and it's commonly like this, right? You take your first three inputs here, you've got x1, x2, x3. So let's say you've got some sort of like three-dimensional input, which means you've got some sort of list of length three with like three different values in it that you're trying to predict something. You're trying to predict some output. You're trying to get a number out of it. Could be a probability of something, could be a category, something like that. You're trying to get it, right? Each of these inputs will have a weight associated with them. So W1, W2, W3. This part here, they all get summed up. So if you've never seen that sigma before, it just means summing W1 times X1 plus W2 times X2 plus W3 times X3. You add your bias term, that's that, and then you get like your linear output, which we termed as Z in the previous slide. You can see back there. So that's why I'm calling it Z. Where in the world did I go? Okay, the linear. And we then run it through that nonlinear function. We have G, and that tells us the output of our neuron, right? So this is a super helpful thing because not only are we now able to model linear relationships, we're now very easily able to model nonlinear relationships because we just need to throw our linear output through some function. We don't have to bother trying to learn some sort of like nonlinear function for ourselves, right? We just throw it into a nonlinear function and go, okay, cool, this should be fun, right? Now, then, given that this is a neuron, one neural network would be a network of neurons, right? But we have a network of neurons, right? Now, this one is actually kind of neural network, all things considered, but like it's just an example. You basically just take a bunch of neurons and shove them together, connect them however the heck you want. Honestly, you don't actually have to connect them this way, but that's what people do because it's fun. And the outputs of the neurons from one group would be inputs of the next group, And each of these groups, each of these like, each of these groups of neurons right here, those are referred to as layers, right? So that first layer would be commonly called your input layer. The last layer is commonly called the output layer. This makes sense. And the middle ones are called the hidden layers because, they're hidden. Ideally, you're not like specifically looking directly at their inputs, you're just kind of looking at what's happening. So that's what I call the hidden. Now, this sort of setup is extremely useful. And it obviously, as you guys know, rating these or stuff like that, obviously these are very helpful for us to model the relationships that we want. But why do we bother with them in the first place? Can anyone think of a reason as to why we don't just go with one neuron, right? Because what I've done now, when I've introduced neural networks, is I went from having one neuron that I said was easier, right? Just a couple weights, bias term, and the nonlinear function, which tell it to do whatever the heck I want. And I've gone and multiplied that by like 100. And now we have a significantly larger amount of parameters and things that we're trying to, work with, right? So why would I do that? Why would I bother having all of these different things when one neuron I said would be useful for modeling the relationship? Anyone think of what? I didn't see something. Check out. More modular. Yeah, so sure that works. It is more modular. It does make it more modular. That's not really what I was going for. Because in fairness, neurons themselves are somewhat modular-ish. It works, but yeah, that's not necessarily what I'm going for. Anyone else? Yeah.
So how they make between neurons along with demonstrate the relationship.
Yep. And actually, you know what? I'm not going to continue because that was exactly the answer I was going for. So, all right, cool. So, yeah, specifically, if you guys if any of you have ever worked in neuroscience, of course, that's it. Not don't worry about it. But when you're thinking about things like literally when your brain is thinking, commonly what happens in the way that you form memories and thoughts and all that stuff is there's just like networks of actual nerve cells in your brain that when you see a certain thing, like for example, when you see a cat, your brain, that specific pathway of neurons lights up and goes, okay, that thing's cute, I'm gonna go pet it. Or if you hate cats, okay, that thing's terrible, I'm gonna go kill it. I don't know, something like that. And so specifically, what happens is that specific neurons in your brain respond to certain stimuli, and those pathways of neurons will respond to specific things and cause specific actions. Right? Yeah. And so what a neural network does is it tries to mimic that, right? So let's say that, okay, I've got some input here, and it causes it travels down this path, this path, this path, and it just gets a really high number here, right? That contributes to this one. However, this other neuron may not be concentrating a lot on that input. It might be concentrating more on something between these two inputs here. So then if this one is very small and this one is very large, it's going to end up not doing too much. Whereas if they're both very large, it will light up a lot and then contribute a lot towards the end. Right? The whole idea is that each neuron learns not an entirely different view of the data, but it learns some different parts of the data. It responds to a different aspect of what you're looking at. And as a result, you're able to model these very complex relationships by looking at them sort of piece by piece. And then analyzing, okay, this part was working, or this pathway lit up, this pathway didn't do too much, that way it's probably, this label here, or this pathway lit up a lot, and this one, but not the other one, it's probably this label here. It'll work in that sort of. But, as I mentioned earlier, it does present us with an issue. We need to choose the best weights and biases for every single neuron here. Now, as I mentioned earlier, this is extraordinarily expensive. And this is why, if you guys have ever wondered why, data centers and stuff have giant server rooms filled with tons of compute power and graphics cards and everything. I can't say this is entirely why, but this is a large contributor as to why. What happens is, if you think about it, each one of these neurons can have n weights. Let's just say it has Sandra, what's the number between 1 and a million? If he's listening and paying attention. I'm going to assume he's asleep. All right, well, I'm going to go with 10. So, assuming that each model has 10 weights, and obviously 9 weights and 1 bias, right? So it's 10 parameters total, right? Because you need to figure out what those weights should be and what that bias should be, right? Well, okay, that's just one neuron, right? And then how many neurons are there? Like, approximately say, okay, this one's 16, this one's, well, it's a large number, let's say 1,000, I don't care. But or actually, no, let's say 100, right? So if you have 10 parameters per neuron, multiplied by 100 different neurons, that is now, yeah, that's not 10,000, that was 10 years ago. That was not 10,000 either. That's 1,000 different parameters, right? That you need to learn just for something small like this. And this is considered, a network that looks like this with like this exact number of everything is considered exceedingly small. Like, in fact, at the point at which we work with machine learning, this stuff you guys do, it shouldn't be small because like for your projects and stuff, again, just like starting to learn this stuff. So, all of them are going to be big too, really. But like, for commonly for like my work, a model that has like 100,000 parameters is considered like extraordinarily small, and it's kind of a miracle that you managed to make something that small that works. Whereas like commonly we'll have ones that have like millions of parameters. I think 49 million parameters or stuff like that. It's like expected sort of deal. It's a lot of different numbers because I mean, when you're trying to model really complex relationships, like for example, one of the projects I worked on was trying to diagnose atrial fibrillation from just someone's ECG wave, so just their heart rate, trying to diagnose whether or not they had AFib, right? That's a very complex relationship, right? Like, I mean, people train for years as cardiologists and stuff to like analyze these waves and see, okay, this person has AFib, right? And so trying to model some highly complex relationship like that, it takes thousands and thousands of parameters and thousands of different neurons and relationships and looking through different parts of the wave and stuff in order to fully understand what's actually going on and actually produce something that is capable of making these relationships. And so if you guys are wondering things like why like commonly like for those of you who are hardware inclined, like if you ever wondered why graphics cards are shooting up when the amount of VRAM they have, or like why universities are spending so much money on this compute infrastructure and stuff like that, or why Apple and all of them are starting to produce produce software that takes up more and more larger and larger footprints on your device, and why it takes more and more processing power, why they have more RAM on their computer. A lot of that is, I mean, okay, part of it's due to like technology, but a lot of that is in part due to the fact that they're trying to cram as much machine learning into their phones as possible. So generally when you're using a phone, it could be doing predictive text while you're typing. It could also be in the background trying to sort through your photos. It could be trying to ping where you are and suggest like, okay, cool. Well, you're probably hungry because it's like 7 p.m. and Lord knows you're a CS person, you haven't eaten lunch. Like, go down to Subway, grab some food. Like there's one 2 miles away. Like they try to do all of that processing power on a very with a very limited amount of resources doesn't exactly work. So that's why all of these technologies are scaling up in terms of the amount of processing power needed, the amount of resource requirements, all of that stuff. Because just in order to compute something like this, you need to run through at least 10,000 different for a small one. And that is, that has a very, very, very high computational load. So with all of that said, that's what makes training these things extraordinarily different, right? Imagine trying to manually go and adjust, you got a prediction, right? You now have to go manually adjust every single one of these neurons, right? I mean, how would you do that in the first place? Like, can you think of a way that you would go and do that efficiently? If you're looking at me blankly, then yeah, that makes sense. There's no good way you could do that efficiently, just by hand, right? You have to go through this giant file or list of 10,000 different numbers and go, well, I'm going to change this from 0.5 to 0.3 and hope it works. Then yeah, that's very, 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 very inefficient. That's going to cause some real issues real quick because you're not going to be able to understand what's going on. You're not going to be able to actually usefully articulate or go through what your neural network is supposed to be doing, right? So, and yeah, I mean, that leads into the way, can you think of a more efficient? Is other than just hand adjusting it, is there a more efficient way of training that you guys can think of? No is a perfectly acceptable answer as well. I will also be taking questions from the Zoom chat whenever they feel it's fine. But you can't think of a way that's cool. Yeah, I mean, these it's hard to figure it out. Any ideas? Nope. Okay, that's fine. That makes sense. So, how about let's think of it this way, right? Last time I went over something called the learning process, right? Which is I don't think this is any textbooks, to be entirely honest, it's something I came up with, but I think it's a good, I think it's a useful way of understanding how to make machine learning, right? So we start out by observing new data, so taking them into the model. The model then assigns them labels, right? And then we see how correct it is. We basically look at the model and we go, okay, yeah, you really don't know what the heck you're doing. That was entirely wrong. And then you just keep trying to do that. You just change the model up a bit and keep doing this process until you're getting your predictions sufficiently correct, right? But the key in terms of actually understanding how you train these machine learning models is specifically in step 3, where we check the correctness of the model, right? What we are able to do, and what we do very commonly, is we use something called a loss function. Now, I want to be clear. I'm not going to talk about any specific loss functions right now. In fact, as I listed on the slide, takes F2022. That's the intro to machine learning course. Great course, love it. Spies is an amazing professor, so I'm not going to testify on that. But the point is that all loss functions do is essentially measure how wrong, right? So they can be as simple as just going, okay, well, I'm going to give you a 0 if you got this wrong. I'm going to do a 1 if you got this wrong, right? And then at the end, you just sum up the amount of, sum up the amount of the numbers you got, so sum it all up. And like how large that number is like your total loss, and that's how wrong you are. So the more ones you get, the higher that sum becomes, and then that's, that shows that you're right. In practice, while it's a kind of useful model, we don't use something like that. We use different functions, I think. Well, I mean, I can name a bunch of them, but frankly, me naming those sounds stupid, but essentially we use different functions that not only tell us whether we're wrong, but they try to quantify how far off we are. So, like in the context of like archery, let's say, right? Like when you're shooting arrows at a target, right? It's not just important if you miss the bullseye. It's important to know how far off you are from the bullseye, because that tells you how much more work you need to put in, what sort of stuff you need to refine in order to get closer to getting into the center of the target, right? Same sort of principle here. We don't need to know just whether we're wrong. We need to know how wrong we are, because that tells us how much to adjust to this, right? So again, if I was off by 1 in my prediction, right? Then okay, maybe I don't need to tune the weights. Maybe I just need to tweak them a little bit, add 0.1 to somewhere, and just go for it, right? But if I'm off by like 1 million, then clearly I'm doing something extraordinarily wrong, and I need to just basically go in the line and start again, right? And so as I mentioned, yeah, this essentially these loss functions, which I'm not going to show examples of because none of them are easy to graph in 2D, and they're all very, very they allow for measurement of error in your model, right? They specifically allow you to figure out how wrong you are. And as mentioned earlier, there's a million different types, and a million more on the way if you look at your research. And it's entirely dependent on the problem type. So, for example, if you're doing something like regression, which is just regression is basically like you have some sort of continuous output. So like you're trying to predict house prices based on the characteristics of a house, right? That's a regression problem because a house price isn't just 10,000, 20,000, 30,000. Worse than that expensive, but like actually more now. But like but it is some sort of it could be anything from like 0 to whatever you want, right? So something like that, you would want to basically you could do you could just do like how far off, right? So if like the actual house price was like 100K and you predicted that it was like 30K, then you would be penalized more because it's a 70K difference than if the actual was 100K and you got it like at 98K or something like that, right? Yes or no? So research wise, yeah, it depends. So in terms of what you guys are going to be doing, in terms of general applications, you don't actually. There's accepted ones that are used for specific tasks. So in the house price one I was talking about earlier, I think the one we use is called mean squared error, which is essentially like the sum of square differences. So you just take the absolute value of the difference, square it, and then you sum that all up, and that's your loss. In terms of classification, the one that's commonly used is something called categorical cross entropy, which Lord knows I'm not going to talk about right now. It's not like it's the most complex math that ever existed, but it is something that just will go over your head if I just go over about it, because frankly, it's just it's basically measuring the probability. It gives you that probability, how rough your probability distribution is of when classes be done. So basically the model will output you've got a 95% chance of being class 1 and a 30% chance, or a 5% chance of being class 2, something like that. And if it was class 2, then it's okay, you are wildly incorrect. you need to fix yourself. Whereas if you get it like 50-50, it's like you're a little closer, you don't need to fix yourself as much. So those are like the accepted ones in certain cases. But if you're working on novel tasks or if you're working on different certain types of problems, then yes, you actually will need to figure it out. One example right now is I'm working on a project with Dr. Chris Metzler on defogging images. So like, while your car is driving itself, there's fog, there's a problem, right? And so one of the things we're looking at is something like, okay, well, there is some sort of model for how like equation for how fog is applied to images or how images get foggy. And so like we try to throw that into the thing and use that as like our forward model for predicting whether or not like or for removing the fog from the images. And so for like custom tasks like that, you will have to create. But in general, and like for most applications, you really don't need to put too much thought into like for like most like just applications where you're just taking a data set and training a machine learning model and you're going, okay, cool, I want to get this. Then yeah, you don't need to really reinvent the thing. But when you start to get a little more fancy, when you start to be like, okay, well, I have a model, but it's like way too biased, and I train it to be less biased in some way, then yeah, you start playing like the loss function. So we're going to move that. So yeah, that's what we do. Any more questions on that front? Nope. Okay, cool. I'm going to take those now. But in general, well, now that we have this loss function, right? It's very clear we just want to minimize this, right? So we have like some idea of like what our loss is going to look like based on each point, and we want to minimize this. We want it to be as small as possible. We want to choose the model with the weights and bias, all of these parameter values that make the loss as small as possible, because that small loss means our models work very well. So how do we do this specifically? I'm not going to teach you that, but I am going to show you this wall of text right here. First things first, if you are looking at this and you want to die, don't worry. That's just kind of how it is. But in general, basically the way that loss functions are minimized. Actually, the first question. How many of you take calculus? There's a calculus at max. Okay, everyone, cool. Yeah, so you all know how to minimize something based on the conversion. Right. Yeah, that's it. But obviously with our loss functions, we're not only dealing with one variable, right? We have multiple different weights, multiple biases, a whole different bunch of neurons they have to work with. So we try to minimize it globally for all of these parameters. And doing so on computers is called gradient. This whole process of how it happens, I am not going to teach you because it is not the most complex math, but it is hard enough that like I would rather leave it to your professors. However, for the fun part for all human computer science, there are actually like, is that 7? No, 6. Yeah, there are literally 6 courses that will teach you independently will teach you how gradient descent and back propagation. And the reason I highlight that is because I took every single one of those courses, and all of them each semester it would just be one of the slides would be, and okay, and so here we're going to be talking about gradient descent. I'm just like, that's I'm good at this point. Like, how many semesters in a row are you going to teach me the same thing? But like if you take that pathway and if you learn, if you take any of those courses, they will hammer in how gradient descent works, how these models are. But what I'm importantly trying to get at here is that we can, as you guys know from calculus, we can find the optimal weights and biases that give you that minimize our loss function. Because we can think of the loss function as just something, it takes in 2 labels, right? One you get from the model, one you get from, you're given training data, and it outputs how wrong you are, right? You can then use, you can then take the derivative of that and you can use that to figure out, okay, which label will give me, or which predicted label will give you the minimum loss, right? From there, well, the predicted label is just a function of your neural network, which is just a bunch of linear models all stacked up together with activation functions all over the place. But point is, it's just some function that takes your training set, or your inputs, and maps it to an output, right? And so what we end up doing then is we just take your loss function as a composition, or you take the derivative of your prediction with respect to all of these weights and biases individually. And then you take the derivative of your loss function with respect to prediction. And then by chain rule, you just multiply them together, and that tells you how wrong you are, and you update the weights based on that derivative. Right? That's more or less how it works. But more or less how it works. And honestly, it's not something you guys need to memorize, it's frankly kind of, but we'll go over this next time. TensorFlow, PyTorch, all of the libraries we're working with will show you how to do it, we'll do it all for you, because doing so is complex. But I just wanted to show you like a little bit of like how it actually works. You take your function, you then take the loss, and it's all the composition of each other, so you can just do chain rule, or as we call it, back propagation, this sort of as we have to advance it. In order to try and figure out what the specific exact weight updates we need to make are, and then start moving the model towards correctness. So with that, well, with that, I'm gonna go towards like the conclusion of this. So we've combined everything. You have your data set, which is a bunch of input output pairs, right? You have your label, or you have your data X, or whatever the X values, and your labels, which are the Y values, right? As mentioned there, each X could be some vector with some number of components, so it has like different numbers for each point to represent like a human or an image or something like that, right? And again, your Y values are just for our case, right? We then run these through a neural network's neurons, which with their own weights and biases and activation functions. And one thing is that the activation function is usually the same for every neuron, because well, we do more nonlinear relationships with super crazy. So we just kind of pick like one for the same one. I think commonly we pick one. It's called random, which we might call rank function. But in general, like you just pick the same one for every neuron and you use that. You quantify how wrong they are via some loss function. You then take the parameters and update them based on how high your loss is, and that process is done through backpropagation or gradient descent. And you just keep doing this whole process. You keep feeding the model with something, get the outputs, see how wrong the outputs are, update based on this gradient descent deal, and you just keep doing this until your loss function is out of it. Right? So before we continue to the next slide on like what part of this whole thing, anyone have any questions about this or any sort of thing they're not understanding? In chat as well. If you feel free to say. Nope. Okay, you guys understood it much quicker than I did. Cheers. I'll take that as a good thing. So with that said, I'm okay. So like first off, I'm gonna hand wave the heck out of this. Like, I'm not gonna actually be gradient descent because like I can't probably just but I'm gonna just draw like a very, very, very small neural network with just random numbers on the board, right? And it's gonna have how many numbers are there? All right, let's just yeah, we'll see how it goes. I'm just gonna draw like one, and it's gonna have like two outputs, right? And basically what we're trying to do is we're gonna try and figure out specifically whether some digit is a zero or not. Right? And so, first things first, I would like to pose a question to you guys. If we're trying to classify whether something is a zero or not, what are some useful things? Now, I don't need pixel values. None of what we're doing is like actually how it works, but just like macro level features. And I'll just hand wave numbers. Like, what sort of things do you think are useful in trying to figure out whether or not something is a zero? Like, what sort of features? What sort of parts of these figuring out whether it's a zero?
If you could like look for an area of black surrounded by an area of white.
Yeah, okay, I was thinking that works, but I was thinking something like smaller level. So like like smaller things. So not just like generally like looking at the whole image and being like, okay, cool. Yeah, if it's a ring of white with like a ring of black all around it and stuff, that's a zero. But like specifically like small portions of these symbols that would be important in trying to classify whether something is a zero or not. Like what sort of like characteristics would be important? For example, one thing that I can say, like this is a motivating example, like if you have some sort of like vertical bar, in the case of like 4 or 1 or 7, it is very clearly not zero because 0 has no vertical function, at least the 0 thing. So we can do something like one of the features would be like I already addressed it, by the way, so I'm sorry. Lines, right? And we'll just go with pick the number of vertical lines in the image to figure out that. So that can be like one of our things, right? I'll go with like 2 more. So like what are other features that would be important to try and figure out whether it's 0?
You could look for like 90-degree angles.
Yeah, sure, so 90-degree angles work. I'm very lazy, so I'm gonna shorten that. I'm actually no that space is out a lot more. Should I give myself more space in the book in general? But yeah, one more. One more. Anyone have anything? Horizontal bars, sure, that works. You know what, I'm just gonna. That one, actually, no, that one. Cool. So I will say one more thing that I personally would have gone with, but I don't actually. Because process, so it's a race crossover, but this, 2 and 8. It's like, yeah, but anyway, doesn't make a difference. That's part of the thing, and that's actually part of what solo was very important. Is the idea of picking features that are important, so finding characteristics that you do actually want to look at is like one of the biggest parts of machine learning. Like before you even get to the very strategic of like models and stuff like that, trying to pick like, okay, well, we want to see like number of vertical lines and 90-degree angles, and then you go through and you're like, oh, this is doing too well, and you go back and you go, oh yeah, we should look across like horizontal crossover as well, and then you try like that's all part of the process. But with just the step that we chose, right? Let's just say this is our initial run. We've chosen vertical line, number of vertical lines, number of 90-degree angles, and the number of horizontal lines, and we're going to feed that through some. I'm going to make my life significantly simpler, and I'm just going to make this the smallest network known to man, right? And at the end, this should output some sort of value that tells us whether or not this thing is 0, right? So let's see. So I'm gonna give you a number from 1 to 3. Actually, wait, no, I'm sorry, 1 to 7. Give me a number from 1 to 3. 2, yeah, sure, thanks. 5, thank you. Cool. We're going to 5. Another one. From 1 to 30%. Thank you. Another one I'm gonna ask for like I'm gonna keep asking. So. 9, thank you. Another one. 23, cool, cheers. Small is gonna be absolutely perfect. Now I'm gonna make another fun simplifying assumption, which is let's just assume that for these 2 neurons here, and by the way, the activation function I'm gonna call that G1 in this case. Let's assume that for this case it's just G1 of x equals x. So it's just identity function. Makes life easy. Just don't have to deal with that one. And then for this one, what am I doing? So I want this output to be less than 1, but I also forgot. Like, there's a function that does this. Okay, cool. You know what? I'm just gonna do it. Yeah. So there's a function that can swap something between 0 and 1. It's called a sigmoid function. I'm just gonna use that. For those who are very inclined, it is. I am plugging this as not that, but yes, that is what that function. That is what the activation function will be for this specific neuron, right? But again, okay, number from 1 to 10. 2, cool. And one last one. 6, cool. So let's take now that we have that. I'm going to bring out my calculator just for when I have to do this, and quickly, for the top left image, right, number 4. How many vertical lines would you say this thing has? 2. Cool. Okay, so for number 4, we're going to be feeding in the number. We're going to be feeding in 2 here. How many 90-degree angles does it have? 3. Yeah, 3 works. Sure. And then how many horizontal lines does it have? 1. Cool. Cheers. So, step 1. We need to calculate everything. Oh shit. I missed it. So How do I do this without making sense? All right, well, whichever the 6 dot will be connected. In reality, this one would be connected here and this one would be connected here as well. But at this point, we're just gonna end up with way too many lines all over the place and it's just gonna get way too confusing and frankly, we don't bother. So, just for a simple example, here you go this. And go with it. Anyway, so for the value of this neuron, right? Remember from earlier, I'm going to go back. Right? For the value of this neuron here, we take the sum of the weighted primes, right? So for the value of this neuron here, we do 5 times 2, which is 10, plus 17 times 3, which is 51 with. Yeah, yes, 51. So we do 10 plus 51 and we get 61 here, right? Now, for this one, again, we do 27 plus 23, which is 50. Okay, right? Since our activation function is the identity function, we don't need to do any fun transformation to these numbers, we just kind of build it, right? Now, next, from here, we then flow forward, right? Okay, so 61 times 2. Why did we pick the largest number? That's 61 times 2, that's 122, right? And then 50 times 6, that's 300. Yeah. So 122 plus 300, we get 422. So we have 422, that's supposed to be C, by the way, which then means that we'll call our output Y, right? Which is sigmoid of the sleep. Which will then be equal to 1 divided by 1 plus 422. It gave me e to the 422 divided by e to the 422 plus 1. Thank you, computer. That's exactly what I want. Totally not that small. Give me a 1. So, in the assumption that this model is modeling the probability that the image of the 4 was a 0, we failed. We have told us that that is a 0. It is not a 0. So clearly we're very, very wrong, right? Now, we're not even just like a little bit, we are significantly, right? Now, in that case, that means okay, cool. We have to go back and reweight everything. We have to change these weights around. Now, this is going to be actually wait. Samra, quick question. If you're awake, you there? All right, I got to do everything myself around here. I want to make sure that they can see this on the Zoom camera. I just realized. But if they can't, I apologize. Try this. Oh God, darn it! That is absolutely illegible. Right. All right, I can't move the camera. Well, shoot, that's awkward. So I'm going to do this, or am I just going to have to go with the should have come in first for this? I'm just going to have to, I can't make the camera move, concentrate on the board. So I'm just going to have to say sorry in advance to anyone who came online. And next time we'll try to make, if I use support, I'm going to try to make it work properly. But with all of that said, cool. Okay. So we got a probability of 1 of a 4 being a 0. That is very clearly very wrong, right? So it shows that we need to go backwards and we need to just bring a timer on my presentation. I'm kidding, but it means that okay, we need to go back. We need to adjust our weights like significantly, right? We've got where our values are. So okay, well let's see. Which pick a weight that you guys want to change. 23. Okay, cool. What do you want to change? Want to change it to 1. Okay, cool. That works. This is not how machine learning works. You have to just figure this out, but I cannot be bothered. So cool. Are there any other weights that you guys want to change? Just erasing values here so we can go through the next image. Are there any other weights you guys want to change?
17.
17, sure. What do you want to change?
3.
3. Okay, cool. We'll do that. And we'll restrict ourselves to 2 weight updates for now because I don't want to bother with the rest of it, but sure, okay, cool. So we changed the words a little bit. Let's try on the other image, right? So let's go over next to the next image, right? What is one? What for one? How many vertical? Yeah, there's one vertical line with number one. How many 90-degree bends are there? 0, right? And that was the worst 0 I think I've ever drawn. Mine was a existence. 0. And then how many horizontal lines? Again, 0. Right? So cool. Let's feed this through the net. Yeah, 5 plus 3. Okay, so that's 5. 5 plus 3, 5 plus 0. Sorry. And then this is just 0. Then you go through here, you get 7, which then means that the sigmoid is just one second, I'll just do this here. Find one divided by 1 plus and then we'll do it. So 7. Oh my god. Stop not giving this position. Cool. All right. So we've got 9, 9, 8. Oh, actually, no, even more certain. So yeah, this model's still absolutely false. Right? So again, we're getting that this is 0.99089. So we still need to go back. We need to change things along. So again, let's pick another way that you guys want to change it. By the way, there doesn't need to be a rhyme or reason to this. I'm not expecting this to actually work. But just like pick another number that you want to change. Real talk, if you're ever gonna jump that big, and it wasn't at your initial step, you would probably restart the entire thing because you clearly fucked up. But for our purposes, we're gonna go with it because it's funny. So we'll change that to 200. Any other weights that you guys want to get changed? What? No, actually, they can be whatever number you want. Also, I realized I didn't include bias terms, but that's just because I didn't. Let's see. Like any other weights you want to change, they can be negative. So yeah. No idea. Okay, cool. So we're just gonna go with changing this to 200. We're gonna go with it. Cool. Okay, now we actually get a 0. I swear this better get actually. I know this is gonna be really funny. So we actually get a 0 now. Okay, so how many vertical lines are in the 0? None. Yeah, obviously. How many 90-degree bends? None, obviously. And how many horizontal lines? None, obviously. So naturally, everything is 0. Congratulations, I played this one. So this is going to be 0. In which case, 1 over yeah, we're going to get it 0.5. Yeah, this so we don't know if that's a 0 or not. We basically left it to a twin flip. Congratulations. But yeah, so as we can, as I mentioned earlier, right, we can really see that this model is just like struggling, like hard, right? And sure, well, if we were actually like updating it in the somewhat of a useful manner, yeah, maybe it would get a little better, right? But still, it's struggling a lot because it just doesn't know what it's doing. It doesn't have enough information. So what would be some potential fixes? Well, I mentioned earlier. First of all, actually connect the neuron properly. But also, as I mentioned earlier, there could be other features that we want to look at. So, for example, number of times that lines cross over each other. Or instead of looking at horizontal lines, we could try and count how many distinct curves there are. Right? So, like in that case, it would be something like this part of the 2 would be its own curve, this part of the 2 would be its own curve, and like certain parts of the 8 would be whatever. Right? You do things like that. You try and look for features that. And what those allow you to do then is you can then just once you figure out those sorts of features, that will then allow you to have a much better understanding of the data, and the model will then will be more, I think the term is expressive, because it just knows more about the data, so it can make better predictions. In reality, I did sort of mislead you on this thing. What we really do is just take the images and like give it a 0, it's a pixel, or we give this number from 0 to 255, or like how bright the pixel is, and we just flatten that into like one very, very, very long vector, throw it in the machine learning model, and it goes. It's like, okay, cool, we know what number this is. Actually not too much, but in general, and for a lot of data that you are going to be using, the idea of picking useful features for your model is extraordinarily important, which is why I want to go over that. Trying to figure out, what we need to feed into the model, what's going to actually make it understand whether or not something is a zero or not, and then going through and just letting it do its thing. That is one of the more important, that's one of the harder parts of machine learning, is just trying to pick those inputs. So, with that said, unless you guys are really desperate for me to go through the rest of these images, which I don't think anyone is, if you are, tell me. With that said, that concludes this meeting. Next time we're going to be, next time, if you have a laptop, please bring your laptop, because we are going to be going through an actual code example, using TensorFlow of how to get it to work. But with that said, thank you guys for coming, and I hope to see you next time. Cheers.